talk about the Fundamental Theorem of Calculus, Part 1, also called the definite integral. So this is basically the definition of the integral, okay? Here's our little integral sign. We end with dx in this case. That's saying that x is the independent variable. These are called the limits of integration. I'm going from a to b. So the definite integral basically says if you take the integral of f prime of x with respect to x, you find its antiderivative and analyze it at b, and then subtract it analyzed at a. Okay? So I think we could agree that the antiderivative of f prime of x is f of x. So it's f of b minus f of a. This is the definite integral. Now, what does the definite integral give us? It gives us different things in different contexts. Let's say that this function right here was a velocity function. Okay, usually we talk about velocity with respect to time, so I'm going to put a time there. Let's put in AB, right? Okay, so let's think about this. What would the antiderivative of a velocity function be? Yeah, it would be a position function. So let's call our position function P of t. So that's going to be P of B minus P of A. What does that look like? That looks like displacement. That's pretty cool. So when this is a velocity function, the definite integral gives me the displacement. Remember, displacement is your end position minus your beginning position, or your change in position over the interval. Displacement. How cool. Let's do another example. Let's say I have f prime of x is the rate at which water fills a tub. Okay. So if I were to take the integral from a to b, well, let's put some times in here. Let's say from 1 to, well, let's go from 0 to 6 minutes, okay? I am filling up a tub of water. This is the rate at which I'm filling up the tub. My independent variable is x. Okay? The antiderivative of f prime would be f of x. So I'm going to do f of 6. My end time minus my beginning time. So what would this represent? Displacement isn't quite the right word, but this would represent the change in the amount of water in the tub over the time period 0 to 6. So this represents the change in the amount of water in the tub. I'm going to run out of room. From 0 to 6 minutes on the interval 0 to 6. Okay? So the definite integral gives us the change in our amount, or the change in our position. End position minus beginning position. Okay? Another amazing and mind-blowing thing about the definite integral is that it is the signed area between the curve and the x-axis. What the heck? Okay, signed area, I say that because area by definition is always positive. Signed area allows us to have positive area and negative area. Signed area between the curve and the x-axis, that is the same as the number that I get when I do the antiderivative f of b minus f of a. Mind-blowing. Let's look at a couple examples of that. Let's go back to a particle moving along a number line. And let's say this particle has a constant velocity velocity of 4 centimeters per second. What do we know about this particle? It's moving to the right because velocity is positive. Let's graph this velocity function just on an xy axis, where y is my velocity measured in centimeters per second and my x is my time measured in seconds. Alrighty, so that's not going to be hard. That's a horizontal line. Okay, there's my velocity. Now, let's say I wanted to find my displacement from, let's say, 0 to 3 seconds. Okay, so here's 1 second, 2 seconds, 3 seconds. 0 to 3 seconds, I want to find my displacement. Well, I'm moving in one direction. I'm moving to the right, 4 centimeters per second. I've traveled for 3 seconds. I'm pretty sure that's just going to be 4 centimeters per second times 3 seconds. Oh yeah, well that's not bad. My displacement is 12 centimeters. Okay, that makes sense. Displacement is 12 centimeters. Okay? Now, I don't know where I began because I didn't give you my starting position. I don't know where I ended. I didn't give you your end position. All I know is velocity. But I do know that wherever I started, I ended up 12 units to the right. That's my displacement. Okay, are you seeing what I'm seeing? I multiplied my rate times my time. We can see that those units disappear. Aren't I just finding the area there? Aren't I just finding this shaded in area? Isn't the area under the curve the same as the displacement? Isn't 12 the same as the integral from 0 to 3 of 4 with respect to time? Let's do this using the Fundamental Theorem of Calculus to make sure that that is actually the case. Let's see, the antiderivative of 4 with respect to time is just 4t. Now, let's review the little notation stuff that we use. One notation we often use is once we find the antiderivative, we write a vertical line. I put a little 0 here and a 3 there. And then I go ahead and I substitute in. That's going to be 4 times 3 minus 4 times 0. I'm just doing my definite integral. So this is going to be 12 minus 0, or 12. Holy cow, that's what we got by finding the area. This, for me, just makes it more intuitive. Why? The area, or the signed area between the curve and the x-axis, gives us the displacement, gives us the change in my position, or the change in the amount over an interval. Let's look at an example of when I'm moving left at a constant rate. Let's say my velocity is negative 4 centimeters per second. So now my velocity is in negative land. So my particle's moving to the left. If I wanted to find my displacement from 0 to 3 seconds, I would find the signed area here, right? So it's going to be negative 4 centimeters per second times 3 seconds. That's going to give me a displacement of negative 12. Okay? And all I would do over here, heck, I could even just put the negative out front, and that's going to give me a negative, which again means in this case, I don't know where I started, where I ended, but my displacement is negative 12, meaning I ended up 12 units to the left of where I began. I hope this gives you an intuitive sense of y, the area between the signed area between the curve and the x-axis gives us our displacement, which then gives us our definite integral. All right, I hope that was helpful.